to reduce aspect coverage redundancy. In web search and recommendation, following papers add diversification factor to results rank. So today I will give you a short overview that uses the spice of two papers called Exploiting Query Reformulations for Web Search Results Diversification, 2010. It's kind of old paper from University of Glasgow. And then as well this follow-up paper, which is from somebody else, but uses a lot of ideas from this original paper. It's called Managing Popularity Bias in Recommender Systems with Personalized Re-ranking, 2019, from University of Colorado, Boulder. So diversified results example here. So here I did a search on DuckDuckGo, and if you have a look, so I searched Apple prices. So at the first position, I get a link directly to the apple.com. Then I get some, Mac computer as an Apple computer. Then I have iPhone repair. And then in the results, I also have prices of actual apples, the physical apple fruits in Walmart. And then as a last result, I also have a stock price of Apple Incorporated. So what we see from this, that apparently this the DuckDuckGo doesn't just give me the top, most relevant answers disregarding, different topics, different interpretations of the query. The query is very underspecified. So what they do is that they give me the most relevant, most probable result, the first, apple.com, but then they also cover the possibility that I'm asking for actually prices of apples or a stock price of Apple stock. So this is so they must be using some kind of diversification of results. So in the first paper, which is about web search exactly, it's called Exploiting Query Reformulations for Web Search Result Diversification. They diversify the results and hope that at least one user will, at least one result will satisfy the user. They find various aspects of the underspecified query. So for example, here it was apple.com, right, was the first spot, but then they also look at apple fruit prices and so on. And they estimate coverage of different of these aspects and redundancy of the documents. And to actually do this scalably, because web search contains there's almost very, very large amount of web pages. So what they do is they, instead of comparing the documents somehow with each other, they use query reformulation. So they take the query, they generate some kind of reformulations of that query, and then they use this trick to reduce the complexity of the problem. The approach they use is an iterative approach. So first they take the first result, which is the most relevant one, but when they look when they look for the second document, they already include some kind of estimate of what kind of aspect the first result already covers, and then they try to select the second result to cover some kind of different aspect, some kind of orthogonal aspect. And then they use this approach iteratively to get to cover different aspects and get more and more results. So they rank them in this way. So the contribution of the first paper is that, as I mentioned before the paper, this idea already existed, but they used similarity between the documents to ensure that there was no redundancy of the coverage of the different aspects. In this paper, they instead split the query into subqueries, which represent the aspects, and then they do similarity between the documents and the actual subqueries. and they are able to scale this much easier. Yes, but that introduces additional problem that they need to know, the similarity between the subquery and the query, but that's handled that can be handled. So how this looks from the mass perspective. So traditionally, the first idea that you're going to get is that you're gonna look only at the relevance of the document to the actual query. So we have this probability, conditional probability of user clicking on the document conditioned on the query. So in this paper, they add this extra addition to the rank. So the result of this is a rank, right? And so they multiply by a small lambda additional term, which is composed of the conditioned on the query, the probability of clicking on the document, but at the same time not clicking, the user does not click at any of the documents that are already in the results above. So this is the additional term, conditioned on the query, the user probability of conditioning on the query, user clicks on the document but does not click on any results above. So this gives me this diversity, right? Because that's the idea that for some reason, yes, the documents are relevant above, but I'm looking for something else that query is unspecified. So I'm looking for some kind of different aspect as a user. And to simplify this, they estimate this query by this formula below. So they sum over all reformulations or over all sort of possible queries from the query logs. They have this multiplication by similarity between the condition to the query. What's the probability of getting the subquery? They have some kind of estimate for this. Then there's also multiplication by subquery. How probable it is that the user, if he queries the query, how the document is relevant to that subquery. And then as well there is this multiplication which represents probability of user not clicking on any of the documents above this result. Because we are using this iterative approach above this result, where the documents where we use this probability of the relevance to the subquery. So they derive this in the following way. So they have this estimate of the sort of similarity between the query and the subquery. They make sure that they sum across all these subqueries to 1. And then they get something like this probability, some kind of estimate of the probability. And so if you remember here, the second term, so they split it into the subqueries. So they have this probability of selecting the document but not selecting any of the above, conditioned on the query. So they split this into the sum of subqueries, and they add this conditional probability. They use this Bayesian theorem here. Obviously, they need to sort of expect that all these queries that they have actually cover everything. And so when they do this, they get this one term that they can estimate, and then they get this other term with the subquery. So, and when they have the subquery, they make this assumption. I haven't seen explanation for this, but I think one possible explanation is that if they make this assumption, they will not make as much error as if they made it earlier. So conditioned on the subquery. So that's suddenly much smaller space, right? The subquery conditioning gives you some kind of much smaller space because the subqueries are always more specific. In this, when conditioning on this subquery, the estimated probability of user clicking on the document but not clicking any of the documents above. by saying that the two requirements are independent, so then they get the relevance of the document to the subquery, and then multiplied by probability of user not clicking on any of the above results conditioned on the subquery. And then when they have this, they add additional requirement that all the results above their sort of the probability of not clicking on them, they are independent, and then they just use this estimate of the relevance of those documents above. So they get this product. So that's how they derive it. It sort of makes sense, except that there's this extra, KPI of this making sure that these two probabilities are independent, and I think that's just making sure that it's just sort of estimate. So how do you generate subqueries? So in that paper they don't generate any of the subqueries, but they have the subquery generated by web search engines, which is probably created from query log mining. They do this by taking sort of the related subqueries plus suggested subqueries from the from web search engines that they can provide to them, provided by those proprietary web search engines. And relative importance of the generated subqueries from this, they use some kind of centralized ranking of the documents that are covered by those subqueries. So they sort of look at when these subqueries are sort of used commonly, what kind of documents are selected, and sort of based on this they are able to estimate the similarity. I will not cover this detail here. Maybe if you think it's interesting, let me know. Yeah. Okay. So if we do this, what kind of results do we get? So in the paper number 1, they looked at NDCG at 20, and they found that if they have this lambda term, this diversification additive here, so if that lambda was small enough, they saw improvement in the results. That's, intuitively tells you obviously that should happen, right? And they observed it in this offline scenario. They haven't done any online because obviously it was academia. They don't have any kind of proprietary platform where they could test it with actual customers. But I think it makes sort of sense. They have some kind of interesting metric to look at. I think it was an interesting paper. So the second paper is called Managing Popularity Bias in Recommender Systems with Personalized Ranking. So here what they've done is that they used the idea from the paper above and applied it to recommendation systems. What they did, they took the document, the web document, and they instead consider it as being an item. Also for them, the query was actually user of the platform, and the subqueries, however, were some kind of item categories. I think that's here's the place where you can decide for yourself what kind of item categories those would be, right? And but in this paper, they use the same equation, except the item categories for them were the split of the categories into three regions, 3 or 2, I'm not sure right now. So they split the items by popularity, and they have this short head, long tail, and distant tail, and those are the subqueries for them. How they actually estimate those terms that we've seen above. So they have this probability of sort of relevance of the document. So they use it to prevent exactly duplicate items. So they use an indicator function there, and that gives them that if the document is already covered, they will get 1, and that makes sure that that document will sort of get 0 extra rank boost. And then they have this. So originally, in the previous paper, we had this relevance of the query to the subquery, right? So here they have conditioning on the user. What is the probability of the user being interested in some certain category? And again, the category probably can be much more things that you could probably apply to different things, but here for them it was the long tail, short head items that that they had in this platform. I think they used movie lens dataset as well for evaluation. And they estimated this probability on the ratio, how the user clicked on those different items previously. You know, how much he was clicking on long tail, how much he was clicking on short head. That's the estimate for this. The results there were following, so they haven't seen improvement in the NDCG, but they also don't see any dramatic drop when they use small lambda. At the same time, of course, they see better diversification, which is probably some sort of soft improvement for the users for long term. You know, you will probably, and as well, of course, this is offline evaluation, so we cannot see sort of actual results in real life on this. But definitely, it seems to be showing that there was at least no harm by doing this. So the conclusion, a ranking method for diversification across aspects of popularity categories was introduced. Interesting idea. And what we found is that from these two papers that small diversification additive to the item rank can improve NDCG in some scenarios, or at least doesn't significantly damage it. So that's all for today. I hope you got the juice, the spice of the paper. Please unsubscribe, dislike, and destroy my channel. And yeah, see you next time.